if you remember last time in the previous lecture, we looked at this stability analysis method called Nyquist, where what you do is you basically define this Nyquist path, which is a semicircle with infinite radius, and project it using the open loop transfer function GH into the GH plane, and then see whether the resulting path or curve will encircle the point of -1 plus 0i in a clockwise manner. Okay, and that is an indication that the system can be unstable. So if we really want the system not to be unstable, we try to avoid this encircling, right? So that's how this relative analysis, stability analysis method is developed. So if you can see here on this figure on the right side, these are the projections of the Nyquist path into the GH plane, these three different curves for three different values of the parameter k, some parameter you can tune in the GH function. And as you can see, for example, if k is small, this is the mapped version of Nyquist. When you make it bigger and bigger, you see this curve is changing, and while for a small k you are not passing through the critical point of -1 and 0i, now when k gets bigger you are now almost passing it, and when k is larger, now you definitely pass it. And since you know that this GH plane curve is symmetric about the real axis, so basically if you have this part of it, this portion of it, for g of j omega, or positive frequencies, then also you have what? You have the mirror image of this with respect to the real axis for negative frequencies, right? So you have also something like this. And so clearly, if there is like more of that, of course there is an extra portion of it, but now if you can see, now I have a loop, and this loop is encircling the point -1 and 0, which means what? Instability, right? Instability. So we don't want this loop to form around this critical point. I mean, like if it's this one here for small k, right, in this system, well, I have something like this. Although I have a small loop, but that does not contain the critical point. So I call the system here that this system is what? The system with the small k, this is stable. This system here is unstable. And then if you have a system that right passes through the critical point, that one is of course what? That is marginally stable. So how can I define relative stability? Relative by defining that how close I am to the point of -1 and 0 where my projected Nyquist path is intersecting the real axis. So if I find this location of the intersection of the curve with the real axis and compare it against -1, the further away I am to the right side of -1, I am more stable, right? So if I have another system like this, which one is more stable? This one or this one? Of course, the one on the right, right? So again, we use the distance between the intersection and point -1, and this distance to the right means stability. If it's to the left, it is unstable, and the more it is to the left means the more system is away from stability. So this is the relative method. So now how do we exactly measure it? So there are two different ways that we can measure. The first one, which you can see here, is called phase margin and gain crossover frequency. The other one is called gain margin and phase crossover frequency. The one that I showed you right now is the second one here, the gain margin. Actually, if I go back and show you one more time, or maybe here. So here, if you look at the Nyquist plot, what I'm interested is, again, this intersection point, right? Where the Nyquist hits the negative real axis. So at that point, what is the phase of the complex number over there? If I show that point with g of j omega, what is the phase of that? What is the phase of g of j omega, which here I'm showing it by angle phi also. What is it? Of course, it is negative 180 degrees or negative pi. So at that angle, I want to know what is the distance, the radial distance, between the point and the origin. So this distance, how much is that? And how do I find it? Yes, by magnitude of g of j omega, right? I get that. And now, if this magnitude is less than 1, it means the system is what? Stable. If it's bigger than 1, it means it is not stable. And if it's 1, it is critically stable. And since I am looking for something relative, so I compare this number against 1. How smaller than 1 that number is. So I define, if you can see here, I define my gain margin. Okay, I define something called gain margin at where the phase of the system is negative 180. I define the gain margin to be, so here, this gain margin, which you can see this word, it is defined as negative 20 log of magnitude of g of j omega, or also 20 log of 1 over magnitude of g of j omega. Okay, so what happens? When magnitude of g of j omega is less than 1, what do I have for this ratio? Of course, this ratio is going to be what? Because, or I can look it here, doesn't matter. What is log of a number which is less than 1, right? This magnitude is less than 1. What is log of a number that is less than 1 in the base of 10? It is negative, right? Or 1 over that number is, of course, bigger than 1. And a log of a number which is bigger than 1 is what? Positive. So now negative times negative or positive times positive, the whole thing will be what? Positive. Right? So a positive gain margin means the magnitude at angle of negative 180 is less than 1. That is a positive gain margin. So we say the system is stable if the gain margin, which is defined like this, we can call it gain margin, is positive. And which system is more stable? The one that has a bigger gain margin. So if I have one system with 10 decibel gain margin and the other system with 25 decibel gain margin, the one with bigger one is more stable. Okay, so, and then what do I call this angle? The angle at which the phase of the system is negative 180. What the frequency, I'm sorry, the frequency at which the phase of the system is 180. What do we call the frequency at which this thing is happening? we call that frequency phase crossover frequency. Okay, so if I go back here, look at the definitions. The frequency at which the phase of the system is negative 180, I call it what? Phase crossover frequency. And the gain margin of the system in decibels is negative 20 log of magnitude of g of j omega at that frequency. If you don't want it in decibel, it's simply 1 over magnitude of the system. But if you want to convert it to decibel, it's negative 20 log of g of j omega at that point. So that's the definition of gain margin and phase crossover frequency. And again, for a system to be stable, we want gain margin to be what? Positive. And again, the bigger positive number means bigger relative stability. Now, there is another way that people will define relative stability, and that's using two other things, or one other thing and the related frequency. So the other method for measuring that is called phase margin, actually, and gain crossover frequency. So what is this one? So somebody came and looked at this a little differently. So what they said is, well, let me redraw it here. So one way to look at it is, if I don't want to encircle that point, wherever I hit the negative real axis, I want the magnitude to be less than 1. That's one way to look at it. The other way that these people looked at it is, well, I want when the magnitude of the system is 1, so they draw a circle with magnitude of 1 unit. And wherever it hits the Nyquist plot, this is where the magnitude is 1. I want to make sure the intersection point, at that intersection point, the phase of the system is what? If you look, it is, the magnitude of it is less than 180. If the magnitude is less than 180, what does it mean? It means this curve will not pass that point, because let's say I have another curve like this, which is less stable, right? So wherever it hits the circle with radius 1, the phase is what? If I look at the phase of that intersection point, the phase is getting closer and closer to 180. And ultimately, if the intersection point with circle of radius 1 is such that it is for this unstable system, now look, the angle for the intersection point is more than 180 in magnitude, of course. So clearly you see, I don't want this phase to pass 180, because past 180 means you're passing at or to the left of the critical point. I don't want that to happen. So that's another way to define it. So how do you exactly define it? I say, well, let's find the frequency at which the magnitude is 1. So I'll find the frequency at which the magnitude of the system is 1, right? Or if I take 20 log of this, what is it? 20 log of 1 is, of course, 0. So I find the frequency at which the 20 log is 0, or the magnitude is 1. I call that frequency, where such thing happening, I call it gain crossover frequency. Then I go and find the phase of the system at that point. I'll find the phase of the system at such frequency, and of course this phase is negative because it is clockwise, but that negative in magnitude is less than 180. So I add some 180 positive angle to it to convert it to a positive degree, and I call this result what? Phase margin. Okay, phi, or we can call it phase margin PM. That doesn't, it's another way to show it. Okay, and that's this angle phi that you can see, that is phase margin. So if a system is stable, what is the sign for phase margin? As you can see, let's say here this angle is negative 150, the angle for the intersection point, but whenever I add positive 180 to negative 150, I get what? 30 degrees positive. So a stable system has positive phase margin, while if the system is unstable like this, what do you have? Let's say this angle is negative 220. So when you add 180 to it, that is negative. So negative phase margin means what? Unstable. And here, the bigger the positive number it is more stable, and a smaller negative number, or in terms of magnitude, a negative number with bigger magnitude it is more unstable. So if I go back, that's the definition here. And you can see it, right? So gain crossover frequency is the frequency at which the magnitude is unity, then the phase of the system at that point plus 180, I call it phase margin. By the way, the way that this one is written, phi and gamma are written differently. So if I go back here, let me correct myself. This one is called phi, and this one is actually called gamma. Okay, so they use the symbol gamma for phase margin and phi just for the angle of the system. Anyway, the important thing is how we calculate phase margin and gain margin, where you can see, and again for a positive system, both of these margins have to be positive, and on a stable system they are both negative, right? So these are different ways that you can define phase and gain margin, and I explain how to look for them in a Nyquist plot. Now you might say, okay, how can I tell in a Bode plot or a Nichols plot whether the system is stable or not, and how much is phase or gain margin just by looking into a graph? Is there a way to do it? So first let me explain them, and then we're going to solve an example together. So first, if I have Bode plot instead of a Nyquist, these are Bode plots, how can I tell whether the system is stable or not and find the margins and the frequencies? So in order to find the gain margin, we have to look for what frequency. Remember, the frequency is called phase crossover frequency, and that's where the phase is negative 180. So I come into this plot and I find the frequency at which what? The phase is negative 180. Then I project that point up to the magnitude like this, and then I look. Here, what is the magnitude of the system? Is it positive or negative? What is the magnitude? So at that point, again, what's the name of that frequency? This is called phase crossover, right? So at the phase crossover frequency, what is the magnitude of g of j omega? What is 20 log magnitude of g of j omega? Is that positive or negative? Clearly you see it is negative, right? If you have a way to, I don't have the numbers here, but all I care for now at the moment is this number is negative. But here it says positive gain margin, but this number is negative. How come? Well, because we define it as what? If you look, the gain margin is 20 log, but with a negative sign. So whatever you see in this plot, yes, although the 20 log is negative, but I'm interested in what? I am interested in negative 20 log. So what is negative 20 log? It is positive. and positive means the system is stable. Okay, now what about the other metric? The other metric I should look for when the 20 log is 0, right? Remember? We look for where the 20 log is 0 or the magnitude is 1. So this is where the 20 log is equal to 0. We call the corresponding frequency what? We call it gain crossover frequency. And then at that point, I project that point onto the phase plot, and I find what? The amount of phase of the system. So what is this phase here? What is this phase phi, which is the same as angle of g of j omega? How much is that? Is that less than 180 negative or more than 180 negative? You see clearly it is what? It is more than negative 180. So when I add this positive 180 to it, what happens? Let's say here is what? Negative 120, 130. When I add 180 to it, what happens? Yes, it is going to be positive. And positive means the system is stable. So that was a positive phase margin, and this guy means a positive gain margin. But opposite of that, for an unstable system, look, where the phase is 180, here the magnitude is positive, but I'm interested in negative of that. So the negative of that is what? Negative. Or where the magnitude is 0 decibel, if I project it into phase, the phase is less than negative 180, it's like negative 200 or so. So even if I add 180 to it, still the phase margin is what? Negative. So if they look like the left side, they are positive. If they look like the right side, they are negative, and the system is not stable. And similarly, I can also look at them in the Nichols plot, where you plot the magnitude versus the phase directly, and you get rid of omega. So here, clearly, this is the easiest to tell, right? Because you can directly see where the magnitude is 0. What is the phase? The phase is clearly, if you consider the sign, bigger than negative 180. So when you add 180 to it, that is a positive phase margin. Also, when the phase is negative 180, if you look at the magnitude is negative, but I'm interested in negative of that, so the phase is positive. In other words, in Nichols plot, if the two intersections, x-intercept and y-intercept, the x-intercept is to the right of this point, and the y-intercept is below this point, and this point is where magnitude is 0 and phase is what? Negative 180. That point is exactly corresponding to which point in the complex plane? Yes, negative 1 plus 0 j. That's corresponding to that. So if I'm passing to the right and below of that, I have both positive. And if I'm passing what? Above that and to the left of this critical point, then both of the margins are negative. System is not stable. Okay? So this is the Nichols plot. Now let's practice one thing together. And by the way, before I get into solving this problem, we said that we want both numbers to be positive. Now, and the bigger, the better, right? The more stable. But we cannot really make these two numbers infinitely big because the system has physical limitations. So what number for gain and phase margins is a good number? It indicates a good stability, something that if a small number changes in the system, a parameter or something, you're not going from stable to unstable. What is a good margin of stability? How much? So for a gain margin, we need more than 6 decibels, or for phase margin, we need between 30 to 60 degrees. Okay, so when the system is in this range, then we say it has a good margin of stability. So now for the system here with this open loop transfer function, 20 times s plus 1 divided by that fourth order polynomial, and h is 1. For this system, I am going to show you, if we really want to find the phase and gain margin and their associated frequencies, how we do it on the paper using Bode plot in MATLAB, or there is actually a command in MATLAB that gives you these numbers directly by passing the system to it. It's called command margin. So I'll show you all different ways to get these numbers. By the way, let me emphasize one more time that these frequencies and the margins are could be a little confusing. So what I want to make sure is you know that the frequency at which we measure the gain margin, the frequency where we measure the gain margin, that frequency is not called gain crossover. Actually, that frequency is called what? It's called phase crossover frequency, because that's where the angle passes 180, negative 180. And also, at what frequency do we measure phase margin? Where the gain passes 1. So we call the frequency for that what? Gain crossover frequency. So just wanted to make sure that this phase over frequency is for gain margin and the gain crossover frequency is for phase margin, not the other way around. So just keep that in mind. Now let's do it here. So first let me show you how to do it the easy way using MATLAB, and then I'll show you the hard way how to do it on the paper. So let's define it in MATLAB. So our transfer function is 20s plus 1 is your numerator. So the numerator is 20 times s plus 1, so it's 20 and 20 basically, right? The denominator is s times s plus 5. The denominator is s times s plus 5, or s squared plus 5s. Convolution of that with another quadratic where it's s squared 2s and 10, right? So 1, 2, and 10. And now we say system is the transfer function of numerator and denominator. So this is my system, and now we can use different methods here. One is we directly use the command margin, and we pass to it the system, which is a transfer function. That is supposed to give me in order gain margin, phase margin, phase crossover frequency, and gain crossover frequency. Okay, so let me show you. That's all I need to do. There we go. Look at them. What is gain margin? 3 decibels. What is phase margin? 103 degrees. What is the frequency for phase crossover? 4 hertz. What is the frequency for gain crossover? 0.44 hertz. Radians per second. I'm sorry, not hertz. The unit for frequencies are radian per second. Right? So you can directly see them. Now let's visualize them in a Bode plot, and then again we go back to paper and I'll show you the paper version too. So first let's look at the Bode plots. So clearly you can say that because both gain and phase margin are positive, the system is stable. But now look at the Bode plot. So this is the Bode plot. By the way, you can also turn the grid on if you want to project better. So you can say grid on. Now, if we go and look, let's see. So if you don't mind, let me copy this figure into OneNote so that I can write on it like this. So what do I have here? Okay. So I'm looking at a frequency where the phase is negative 180. So let's find where it's negative 180, and that's the frequency. This frequency is called phase crossover. And how much is it? If you project it down, you see that this is 10 to the negative 10 to the 0, so that is 1. This is 2, that is 3, that is 4. It's almost 4, right? And if you look at the MATLAB return, it is 4. And then it says at that the gain margin is 3.13. Is that the case? Let's go look. So at that frequency, if I project it up there, and then now project this onto the horizontal axis, if you zoom in into this number, you see this number is negative 3.13. But again, remember that gain margin is negative of the magnitude. So this means the gain margin is positive 313. And I can show you, I can zoom into the plot and show you. The other metric was when the gain is 0, the magnitude is 0, and that is happening almost here, right? So again, this was W phase crossover. Now this is where the gain is 1, so this is W gain crossover. And then at that frequency, first of all, how much is it? So if you go down, what is that? So this is 10 to the negative 1, so it's 0.1. That is 0.2, that is 0.3, that is almost what? 0.4, close to 0.4, right? And again, you can see that's the case, right? It's 0.44. And we expect 103 or 4 degrees phase margin. So let's take a look here. So if I project that point right onto the phase, this is the phase of the system. If I bring it all the way to the left, right? And if you see here, this angle is clearly bigger than negative 90 degrees. And if we zoom in, you're going to see that angle will be 180 minus 103, right? So it is like, it should be like negative 77 degrees or so. Therefore, the phase margin is going to be like positive 103. Just add 180 to it. And this is positive and this is positive. So from both of these, I can say the system is stable. Okay, so, and you can see it here. If you want, you can use the data tip as well and click here. And then try to move it where the magnitude is close to 0. You see right now it's 115. If you move to the right, now you are almost at 0. The magnitude is 0.02. And what is the frequency? 0.44. So clearly you see at 0.44, that's where your magnitude is almost 0. So that is your phase crossover. And then use a data tip here at the same point, right? So you come here and click at the same point, and you see at the very same frequency, what is the phase? Yeah, it's almost negative 77 degrees. And then add 180 to that, and then you get 103, 104. Okay? By the way, each point in the top plot has a corresponding point at the same frequency in the bottom plot. So you can exactly click at the same frequency. So this is your phase margin, and then you can come here and find where the angle is negative 180, which is here. there are 2 points on the 2 sides of it. There is nowhere exactly on it, so you either go negative 172 or negative 186, unless you use, as I said, a large range of frequencies. This plot in default in MATLAB does not use a ton of points, but you can pass to it a lot of frequencies. And you clearly see the phase of the system, the gain of the system is what? So let's use one of these points, maybe 186, and now I click on the corresponding point here, right? You see the frequency is the same, 4.2, and the decibel of the system is negative 11. If I jump here, it's negative 8. So somewhere between negative 8 and negative 11, and then negative of that should be 8 or 11. But I guess the system gave me, the command gave me a smaller number. As you see, the gain margin is 3 decibel here, which is quite weird with that plot. So here, to just make sure that the numbers are correct, I defined more points for the Bode plot. I used the command log space of between 10 to the negative 2 to 10 to the positive 2 using 1,000 points. And then I ran the command Bode of sys with this omega, and then I got a much finer plot where now you can move very smoothly on the curve, not jump. And you see I could get the phase exactly at 180, and you see the frequency is 4 point, and you see the gain margin is the negative of that, which is 9.88. So the gain margin should be 9.88, not 313 or so. So that command gave me one of the answers wrong. And also the system for phase, you see that the magnitude here is almost 0 at this frequency, 4.442, and the phase margin is 180 plus this number, which is 103.6 degrees. Okay, so that's what I have. And so you see this command did not exactly return the correct number. Now what I want to do, and I want to show you, if we search the command margin, let's see if we can pass a range of frequency to this command too. And you see what you can pass to it is magnitude, phase, and omega, or directly a transfer function. So it says you get the magnitude, phase, and omega from a Bode command and then pass them so that this command can calculate it for you. So let me now redo it, and hopefully I get better numbers. So I say magnitude and phase is equal to Bode of system with these 1,000 points. And now that I want to call the command margin instead of sys, I say what? Use the magnitude, the phase, and the frequencies that I gave you from the Bode command and give me these numbers back. And you see still it is calculating gain margin wrong. The others are good. This is 4.01, this is 0.442, which what I found over here. The phase margin is right, but somehow the gain margin is wrong, and that is very weird because I use this command a bunch, and typically it gives the numbers correct. So the moral conclusion of this part is try to use Bode plot and find the numbers from Bode plot. Do not rely on this command for all of the numbers. Sometimes it might give you a wrong number. But that is an important error to see so that you know what to do. Now, I said you can always refer to the paper and do it on the paper. Well, how? So in this case, my transfer function was, so gh of s or g of s was 20s plus 20 divided by, and In the denominator we have 1, 7, 20, 50. 1, 7, 20, 50. Okay, so that is my transfer function. Now, what do I want? Let's say I want to find where the magnitude is 0, find the phase, and then find the phase margin, or the other way around, find where the phase is negative 180 and find the gain margin. So if I want to calculate the one that the MATLAB gave me wrong, that margin command, I plug in, I want this. I want this to be negative 180. And the question is, well, if everywhere over there I plug in for S j omega, what is going to be the phase of that system? Well, if we plug in j omega in the system and simplify, what do I get? So from here, gh of j omega will be what? It is going to be 20 plus 20 j omega divided by, and then wherever we have power, we try to simplify it. You know, for example, j to the 4 is positive 1, so it's going to be omega to the 4. That's the real part. And then this square part is also real, right? Any even power is going to be real. Any odd number, odd power, will be imaginary. So it's 20j squared, which is negative 20. And then plus j times. And now the cubic part will be negative j times 7 omega cubed. And this part will be positive 50 omega. Okay, so this is gh of j omega, and now what is the phase of this? Phase of that is the angle of the numerator minus denominator. Angle of the numerator is what? Tangent inverse of 20 omega divided by 20. And then phase of the denominator is tangent inverse of the imaginary part divided by the real part. This should be equal to negative 180. And now your job is to solve for this equation, and for this you need to know trigs. Okay, I give you a general idea. First, these two can be cancelled, then you can cancel out 1 omega from here too. And then what you do, you take tangent of both sides. And then use this formula that tangent of A minus B is tangent of A minus tangent of B divided by 1 plus tangent A times tangent B. So use this trig formula. So here you call this one A, you call this one B. And you can solve for it. So, and why is it good? Because tangent of A is tangent of tangent inverse, and tangent inverse would cancel each other. So this tangent of A will be simply the argument inside it, which is simply omega. So it is going to be what? If I use this formula, tangent of A is simply omega. Tangent of B is the argument inside it, which is 50 minus 7 omega squared divided by omega cubed minus 20 omega, right? That's tangent of B, the argument inside when I simplified an omega, divided by 1 plus tangent of A times tangent of B. This whole thing should be equal to tangent of negative 180, and you know tangent of pi is 0, or negative pi. So what does this mean? It means when a whole ratio is 0, then the numerator is 0. So this guy should be 0. And I guess you can simplify now, right? So you can say, well, if I do a common denominator, I'm going to get omega to the 4 minus 20 omega squared minus 50 plus 7 omega squared. This whole thing divided by omega cubed minus 20 omega. This is 0. Again, the numerator is 0. And the numerator is going to be omega to the 4 minus 13 omega squared minus 50 is 0. And then I need to solve for this, which I guess everybody can do. So if I solve for this omega, you will get this number that we found, where it is about 4.01. Just plug in 4.01 in it and you'll see that it will fit. You can try it yourself. And now, how do I find gain margin? Well, at this frequency, I need to find the magnitude of this one. And what is the magnitude of that? The magnitude of g of j omega is the magnitude of the numerator. So you have 20 and that, so it's the magnitude of numerator, which is square root of 20 squared plus 20 omega, the whole thing squared, divided by the magnitude of denominator, which is the real part squared, plus the imaginary part squared. This thing, you calculate this value at what frequency? At 4.01. And then whatever number that you get over there, then what is the gain margin? The gain margin is negative 20 log 10 of that number. So if you want, I just plug in 4.1 in this, and let's just do it just to make sure. Okay, so here I have done it. I defined the frequency, defined numerator, denominator, square roots, divided 10 take to negative 20 log, and you see that's 9.9, which is what I found in the Bode plot. So do not just rely on that 3 decibels that MATLAB returned. Okay, so we could do it all on the paper. And again, as I said, you can then go ahead and calculate the same way the phase margin, right? So you can just find the frequency at which the numerator is 0 and then plug it back into the phase formula, which we had, correct? This one. And from there you can find the phase margin. So the next topic that we have to discuss briefly is, okay, so far whatever we have seen in the frequency response was related to steady state response of a system, right? Because if you go back to the very first slide, we said the frequency response is about the steady state response of a system to a harmonic input. And you might say, well, what about the transient response of the system? Can we say anything about that from these frequency plots? And the answer is yes. For a second order standard system, there are some stuff that you can tell. So if you remember, the standard format for a second order system of output over input was, if you remember here, let me show you. So if you have the input, output, and here you assume that the system is unit feedback, right? And this is R and this is C. The transfer function, closed loop transfer function, was omega n squared over s squared plus 2 zeta omega ns plus omega n squared. And this is also equal to what? G over 1 plus GH, and H here is 1, so it's equal to this. So you might wonder, okay, what is G such that when I calculate G over 1 plus GH, I get this one. And if you from here calculate G, you see that G is actually this quadratic function here where there is no constant term in the numerator, right? So it's just omega n squared over s squared plus 2 omega n zeta s. So except for this, basically. If you plug in that here, you're going to get this closed loop transfer function. So now, if this is the open loop transfer function and I'm drawing the Bode plot for this system, from that Bode plot, how can I find the values of omega n and zeta? And you know, when I find these numbers, every one of the performance characteristics for transient response, including what? The rise time, including the peak time, including the maximum overshoot, including the settling time, and so on. All of these guys that we learn, or delay time, all of these that we had in the transient response, they were all related to what? Omega n and zeta. So if I can find omega n and zeta from a Bode plot, then I can find all of the transient response performance characteristics. And the question is how? Well, if we look at the phase plot of the system, for example, so here, this is what we did. We tried to calculate phase margin of the system. So we calculated where the magnitude of the system becomes 1. This is the frequency at which the magnitude of the system, so magnitude of g of j omega, becomes 1. We found that it's not hard to show that at this frequency, the magnitude becomes 1. And then at that frequency, we calculated the phase of g of j omega. And then we found this formula. And then we added 180 to the phase to get what? Phase margin. So this is the very important formula, that the phase margin of the standard second order open loop transfer function is equal to tangent inverse of 2 zeta over square root 1 plus 4 zeta to the 4 minus 2 zeta squared. And if you plot that versus zeta, you're going to get this exact curve. And it's interesting that for a range of zeta between 0 to 0.6, which is here, in this range, the relation between zeta and gamma is almost linear, not perfectly linear, but almost. And you can say that gamma over 100 degrees is almost zeta, so the slope is 100 degrees. For example, so if I say the gain margin is 30 degrees, phase margin, I'm sorry. If I say the phase margin is 30 degrees, what does it mean about zeta? Well, divide 30 by 100, zeta is what? 0.3. Whereas 50 degrees is almost 0.5, right? Approximately. Can I calculate it exactly? Sure. All you need is just find this angle here, right? So I have this as like 60 degrees or so. And then I solve this equation for zeta. So I need to take tangent of both sides and then solve for zeta. And I can do that and find the exact value. This is the best approximation to the solution, but you can also find the exact value. So yes, if anybody gives me phase margin for a second order system, what can I give you back? Zeta. Okay? And if anybody give me where the magnitude becomes 1, what's the name of this frequency? Yes, this is gain crossover frequency. If somebody gives me gain crossover frequency, then if I have zeta calculated from phase margin, I'm gonna plug it here, and then from there I can find what? Omega n. So once I have those, I can calculate all transient response performance characteristics. And not only that, I can also, when I have omega n and zeta, I can also calculate the resonant frequency and the resonant magnitude for the closed loop system as well. Okay, So you can look at all of that. Okay, so I guess we already passed 5 minutes of our lecture time. Sorry for that, but I need to go over a little bit of board work. So I'll see you in our next lecture. Thank you.